welcome back. With great pleasure, I want to introduce the next speaker, Lyuben, who's from the Bulgarian Academy of Science. I have some previous experience with the Bulgarian Academy of Science, and they definitely want things to happen in Bulgaria and a lot more people to get engaged with science in Bulgaria. I personally met him today, but let's see what he will tell me about LOFAR, because I've heard a few times about LOFAR, and I think it would be very interesting for you to hear it as well. So please, warm welcome to Lyuben.
Чувам се, да. Ще направя една кратка интродукция на български и после лекцията ще продължи на английски. Казвам се Любен, по професия съм софтуерен инженер. Занимавам се главно с данни, които наблюдават агрономически полета, но и също с изграждане на приложения. Освен, че съм учил в Единбург, Обединеното кралство, компютърни науки, в момента съм четвърти курс в Софийския университет със специалност Астрофизика, Метеорология и Геофизика. И имам огромен интерес към изследването на Вселената и използване на различни технологии, за да се изследва Вселената. Това е накратко за мен. Също така тази година започнах стаж в Българската академия на науките. В този стаж ние наблюдаваме, така да се каже, Слънцето и използвайки огромно количество данни, обработваме тези данни и ги класифицираме, дали те са добри да се прави наука върху тях. Накратко това е на български, сега ще променя на английски. Hello to everyone. My name is Lyuben, and I'm a software engineer. That's my profession, but I'm really interested into science, and right now I'm studying physics in Sofia University. And I'm an intern in the Bulgarian Academy of Sciences, working mainly on observations of the sun and using machine learning methods to analyze data and to classify specific data of the sun. So my presentation is called LOFAR Bulgaria and Machine Learning in Radio Astronomy. So in a couple of words, there's insane amount of data that's coming from space to Earth, and it's basically electromagnetic waves that are coming from very distant sources. And not up until the last century, radio astronomy was something that it was predicted by James Clerk Maxwell in his theory of electromagnetism, but it wasn't actually found scientifically up until the last century. So radio astronomy gives us a way to look into the distant universe, or to look into space with different eyes. So the radio waves, they are very big wavelengths, but very, if you would say, big waves, the radio waves, and they give us the ability to look, for example, into the middle of our galaxy, or into very distant pulsars, or the ionosphere, for example, of Earth. Look at the sun, different objects, and just give us the ability to look at the universe with different eyes. So what is radio astronomy? Radio astronomy is the study of natural radio emission from different sources all over the place. The range of frequency is between 10 megahertz and 1 terahertz, and nearly everything in the universe emits radio waves. Even we emit radio waves. And in a sense, because the radio waves are very specific, we are able to look at, as it said here in the presentation, a parallel universe containing unexpected new objects. And here in the presentation, there's a textbook in radio astronomy, so you can learn all about it. If you want, I'll send the presentation to Lacho. Okay, so in a sense, what's happening? In order to get that electromagnetic radiation, we need to have a certain type of hardware to get that signal, and then to use certain type of transformations in order to create an image. And why are we using radio astronomy? You can definitely see it here from the picture, when you can see the big satellite dish, which is between maybe 5 centimeters up until 10 meters. So on the x-axis you have wavelength. So this is the size of the wavelength that we're observing. And on the y-axis you have the atmospheric opacity, or how much our atmosphere lets us see things. So for example, as you can see on the left side, the gamma rays and x-rays, ultraviolet, they're all blocked by our atmosphere. Thank God, because we would be dead if gamma rays or x-rays are coming into Earth. So basically the atmosphere is like a shield. It's protecting us from cosmic radiation that would otherwise kill us. And then we have the visible light. You can see here the rainbow. And then you have near infrared, that some of it there is a way to observe, but most of it is blocked because of the clouds. So I mean, the clouds are also kind of not letting us observe in near infrared. But if you want to make radio observations, the clouds are not in your way. So the thing about radio astronomers is they can do observations 24 hours a day, and nothing will get in their way, because the radio signals can penetrate the atmosphere. I mean, that's not always the case, because we have the ionosphere, which kind of stops some of that radiation, but we'll get that in a little bit. So just to say a short, you're able to observe the universe with radio telescope from anywhere that doesn't have that much radio pollution. Because as you know, our communication systems are mostly in radio, and like, for example, communicating to somewhere happens to radio waves. So if you're near a place where a lot of communication is happening, a lot of mobile phones, a lot of other communication, then it will be very difficult to make an observations, because you will have a lot of noise. Okay, so there's also a link to another course here where the image is taken, and you can have a look afterwards. And let's talk about a little bit how we're doing these observations. So LOFAR is, as it's stated here, it's a pan-European low-frequency radio telescope that's distributed all over Europe. So you have all these points that you can see here, they're all different radio telescopes. But in the past, radio telescopes were big dishes, like massive dishes that were taking the radiation, the electromagnetic radiation. Nowadays, radio telescopes look a little bit different, but we'll get that in a little bit. So as you can see, LOFAR is able to observe from low frequency up until from 10 megahertz up until 240 megahertz. And it was developed by the Dutch Institute of Radio Astronomy. So this is an international consortium that's working throughout all Europe. And basically, it's connected of exploring early distant universe, solar activity, and our atmosphere for some specific processes that happen in our atmosphere. So this is what one of the LOFAR telescopes is. On the left side, you have low-frequency antennas. These antennas actually they're not very difficult to complete, but essentially they're very, very good. And if you see how they're distributed, that's in a special position or in a special way, so we can get a better image. So basically what happens is we're looking at the same source from different antennas, and we're getting a better image because of that. So there's kind of a the signal gets all connected, and then you get one single image. All this data from these antennas gets stored here, and then maybe through some pipelines or something like that gets used by scientists all over the place. So, but mainly from the Astron Institute. And these here on the right side, they are the high frequency antennas, which are kind of isolated in a specific way, so they can get observations very good. So what is the radio telescope observing? So multiple things are observed. You can see the planets. The sun specifically, from my opinion, is the most important object in the universe. Why? Because without the sun, we would be dead. And we need the sun. So, and we also are kind of dependent on it, because if the sun kind of bursts an insane amount of radiation, it will affect our communication. I mean, some communication can completely stop because of that. And for me, the sun is the most important object in the universe. We also have the ionosphere of our beautiful planet, which is basically a layer of our atmosphere which has a lot of electrons. And these electrons are there because the solar wind is hitting the atmosphere. And when the solar wind hits our atmosphere, or that's like gamma radiation hits the atmosphere, some of the electrons get kind of distributed out of the atom, and the ionosphere is basically just a layer of electrons which exists in our atmosphere. And you also have cosmic magnetism, pulsars, and like very, very interesting like black holes. This is kind of nowadays is very interesting to observe. Like basically almost everything. There's also lightning, meteors. So there's a lot of things that we're observing using the radio telescopes. LOFAR, Bulgaria. This is a project that is led by my tutor in the Bulgarian Academy of Science, Associate Professor Kamen Kuzarev. He worked a lot for this to be reality. And right now, at this moment, I mean, you can't see here, but this is Bulgaria on the left side. And Bulgaria will be part of this European consortium. And right now, in a collaboration with Technical University, Sofia, a new telescope is created near the Rogin Observatory. And we will be able to be part of this amazing telescope, to be able to conduct scientific research, to focus on specific objects in the universe that we want to explore, using our data, not data from different countries. So this is extremely important. So right now, we're going to have an extreme impact on science in Europe and also in the world. So as you can see, it's very important where these places are. Specifically, they are places which you don't have that much radio noise. And that place for Bulgaria is Rogin, close to the other observatory that that you know about. And so that's pretty much long story short about LOFAR BG. But yeah, join us on this mission. Learn about radio astronomy. There's an introductory course. You can learn about data handling and analyzing very, very big data. So why this is important? Every day we have terabytes, even petabytes of data coming from the universe. We need to know how to use that data in order to conduct scientific research. We need to know how to use data pipelines to transform the data using specific methods, Fourier analysis, and etc., etc. So we need to know how to handle all of this data. And you also get the opportunity to contribute to real scientific research and be part of international science publication. This is a link to our internship that we offer. It's very good for students who are interested into applying technical knowledge. I mean, this is the Technical University. This project is also in collaboration with the Technical University of Sofia. This is the Technical University of Sofia branch Plovdiv. So if you want to be part of this amazing project that's happening right now, then give us a shout. Yeah, just send me an email or send me a direct message. mean, my contacts will be with Lucho. So yeah, if you're interested into joining this amazing mission in creating actual impact in science, then contact me. So what am I doing exactly? The colleague before me very well explained that nowadays people use the word artificial intelligence, but most likely the word should be machine learning. Because what are we doing? We're taking some data and then we're giving it to the machine. And then the machine needs to make some kind of a decision about that data. And so how would the machine make a decision of that data? Well, we will use a specific labeling or classification that my colleague before me explained to let the machine know that this data, for example, is good or bad. So what we did was we analyzed and grouped the solar data to understand how we can detect outliers and anomalies. So we have this data of the sun. We would want to say if this data is good, if we can see the sun, or if we're not able to see the sun. And then classify the data using the machine learning algorithm if it's good versus bad. We also detect ionospheric interference using this model. Another thing that we're also doing is, which is not in this presentation, but we're also detecting if the sun is active. So if there's an eruption of solar radiation, then we have a certain threshold that we have let the machine know. So if the sun radiation is over this threshold, then there must be solar activity. So this is also another project that we're working on, but it's not in this presentation. If you want to learn more about it, then you can contact me and we can discuss more about it. What has been done? We created, basically the data that we're using right now is the Astron data. So this is data taken from the Netherlands or from different countries, maybe Ireland or something like that. And then data taken from multiple instances. We take this data, we download it onto our machine, and basically we put it in a specific form, or you would say data type, in order to be able to analyze it. What we did was we researched some algorithms, how that data could be analyzed, and what is the most important about this data. So this data, what it is, it's looking at the sun in time. So it's a time series data. What we did, we created functions to group the data based on the identification. So let's say based on a specific observation. We know that 1 week ago there was a solar eruption of insane amount of radiation, which is also connected to the sunspots. We get the data for that, and then we start to analyze it. And then we group it into specific time series and frequencies. Why is that happening? Because in different frequencies, you have different observations. Why? Because as you saw on the slide before, the atmosphere only lets certain frequencies to go in space. It blocks other frequencies. And then we displayed some temporal trends of the data in order to analyze it and to plot, to find some outliers or to find bad data. And then compared it with the original observation. After our data analysis, we conducted the machine learning. And based on some specific statistical features of this time series, we classify a time series if they're empty, good, or bad. So in a sense, this will help us as scientists working on solar data. In this way, it will be a lot easier for us when we're getting the data to clean it. So what we have been doing is a way to clean the data from bad observations or from like let's say something happened with the hardware, it's not working as expected, then it's just an empty observation. So this in a way helps us clean the data. This is just a part of our data analysis. So this is an observation that is taken on the 3rd of March this year. So that's about 6 months ago. We know that this observation is, we know that this observation is connected with the solar activity. And here you can see different different information about the solar activity. This is in very low frequency, and this is in higher frequency. So let's go again. I want to show this video. It's actually quite important. So this is actually the high frequency observation. You can see the sun in the center, and you can also see how it's erupting radiation. You can see how it gradually increases, and it becomes very large at the end. So this, we know that the sun is active. Then the next observation, if I can go to the next slide. It's absolutely the same observation, as you can see here. It's the same observation, but it's in a different frequency. You can see it's a lower frequency. But you're not able to see anything on this observation. You're not able to see the sun. You're not able to see anything. So this is bad data. This is not very good for us. And then using our machine learning model, we also, during the analysis, we found this data which is empty. So there's no signal here. Okay, let's continue. And then this is what the data looks like. So there's no signal. This is just an observation, 2023, the 5th of March. So maybe there's something wrong with the antenna or something like that. And then let's continue. We also conducted some outlier analysis to find some outliers, let's say, in the data, which can be easily shown here. So in this video. So this video basically shows you a very high frequency. You can see a very high frequency, but the signal is not very good. You can see that there's some distortions here in the signal, which doesn't let us observe the sun. So there's something happening right now. We don't know what it is, but we don't get the data as we would expect. And then, okay, next slide. So what we did, we labeled the data in good, bad, or empty, and used some statistical features to classify this data. We make sure to go through all the data, all the images that we have, and all the time series to label them. Part of the images is for training, part of the images is for testing. So after we labeled the data, we trained the model. We used these statistical features like mean, standard deviation, and other statistical features in order to label it. And then we used the random forest algorithm in order to train the model on this data. Basically, the labeled data was split into training and testing set, and then we gave that data to the model, which is labeled. So the testing data is not labeled, but the training data is labeled. And then what happened? The initial results were over 80% accuracy. So we have 80% of our observations were labeled very good or labeled as expected. But then, as you can see, that these results indicate that the model is particularly effective of identifying good and empty observation, but it's not very good for bad observations. So we went back and we said, well, what can we do better? And then we figure out that in order to improve it, we need to add more statistical features. So we added more statistical features into the model. And then what happened based on that improvement and based on that feature analysis, we revealed that the most significant contributors to the model predictions were the minimum value, the mean value, standard deviation, and the proportion of zeros inside the time series. And then these are the results of our supervised learning algorithm. You can see here the accuracy of the model is 0.99, so that's insane accuracy here. You can see here our statistical importance, and you can see how it goes for good observations, for bad observations, and for empty observations. And then after we trained the model, what we did was we started classifying new data. So data comes to us every day. Every day it comes to us. And what we did, we model that data into a specific data frame, and then we pass it to the model and say, please classify me this data. Let me know if there's good, bad, or empty data inside of it. The results were very good. We can see here on the bottom side, we have 179 observations here, which are good. Here you can see the identification of that observation, the frequency which is done, and then the classification label here. If it's good, 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 and then you also have bad, you also have empty, and etc., etc. Our future endeavor is to build on top of this labeled data and to build a convolutional neural network that classifies each image. So right now we're classifying the whole time series. We're looking at one observation as a whole time series. For the future, we want to extend that. We want to look at each image and say, this image is good or this image is bad. The idea that we have is to use this technique to fuse the convolutional neural network with the statistical indicators to improve the image classification. This is actually the most important slide. Right now, there's a couple of research that are happening. The first one is observing the ionospheric interactions with the solar wind during solar activity from the island Livingston. So this is in Antarctica, and it's actually with a colleague from the Technical University of Sofia. He will go in Antarctica at island Livingston. He will put an antenna there, and they will be looking at the ionospheric interactions, and then we'll be able to use the data and to do some science with the data that we're able to get there. I mentioned about building the new telescope. You can check it out on the website, LOFAR Bulgaria. And then, as I mentioned, we're doing some machine learning for detecting solar activity and ionospheric interactions with the Earth atmosphere. Thank you for your attention. Any questions?
Okay, so in the first slides where we saw the antennas, the high frequency ones were well structured, while the low frequency ones, yeah, exactly, yeah, that's one. The low frequency ones are not really ordered well. Why is that?
Actually, they're very well ordered. You think that they're not ordered, but there's a specific algorithm because, as you know, the Earth is rotating right now, and it's also tilted. So this way that they're ordered is the best way that they could be ordered in order to get the best image resolution. So you can look at it like it's random, but it's actually structured in a specific way in order to get the best resolution of image that you possibly can for that specific location on Earth. So this is related to the location, the latitude and longitude of the observatory, where this, I think this is in Norway, if I'm not mistaken. But yeah, it's actually ordered in a specific way in order to get the best image resolution.
And one more question about the longest radio waves. Why are they blocked by the atmosphere?
The longest, they're not blocked.
Because
sorry, let's.
yeah, here.
You mean the long wavelength? Oh, these ones.
Yeah, the last ones. Exactly.
This is probably connected with the atmosphere and basically the elements inside the atmosphere. Maybe it could be clouds. It could be, which basically what's happening is the radio wave is going and it's not able to penetrate the atmosphere. It just gets reflected, or it just stays inside Earth. So it's in connection with the elements inside the atmosphere and the radio wave. So if it has a specific type of energy, basically what will happen is when it approaches a specific atom, let's say hydrogen or maybe ozone or something like that, or nitrogen, or basically what happens is the wave hits the particle, and there's three different things that could happen. It could happen a photoelectric effect, it could happen beta decay, or it could happen maybe a reionization. So it's basically connected with the specific particle and how it interacts with the atmosphere and the energy that the radio wave has. Does this make sense?
Yeah. Thank you.
Any other questions?
Yeah, so my question is more related to the impact of humans' activities in space on radio frequency and radio astronomy. Do satellites, especially like CubeSats and the growing number of CubeSats, actually impact in some way low frequency antennas, the same that they do with some of the higher frequency astronomy and also the visible light astronomy?
Yeah, that's a very good question. Yeah, so the more satellites we have in low Earth orbit, the worse it gets for radio astronomy. And actually, Starlink is, you know about Starlink. It's so bright that it's blocking our observations. So every time the Starlink satellite passes, we have some distortions, or we're not able to observe anything in a specific frequency, as you mentioned. So it's really important that we advocate for that we say that we need some specific wavelengths that are going to be used for science, because otherwise everything is just going to be blocked by terrestrial usage, you know. So but yeah, that's actually a very big problem. And I read about a very good publication from the Netherlands, from the Astron Institute, specifically about that. And he mentioned that these satellites are blocking our observations, and it's we need to find a way how to get a specific wavelength that they should not or they should not go through that specific area in order to block our observations. So that's actually quite important, and we need to advocate for this. We need to somehow find a way to work with Starlink in order for them not to block our observations. But yeah, that's a great question. Thank you.
Okay, last question.
Okay, I just want to ask once again about the ionosphere on the next slide. Can you explain a little bit more precise here how the ionospheres actually react to observation and for the process?
How it reacts? Well, basically, the solar wind is bombarding the Earth with insane amount of radiation, and this radiation spans from gamma rays up until radio very low frequency, and a very high frequency, sorry, and low frequency. So from very high frequency to very low frequency, the sun, actually here the sun is bombarding with the solar wind the magnetosphere and the atmosphere. So the atmosphere is actually quite long, and basically what happens is this radiation hits firstly the magnetosphere, and then from the magnetic lines it goes into the polar regions. So both polar regions are insanely bombarded with any type of radiation. So the more you go to the polar region, the more radiation that you will have on Earth. So that's firstly the magnetosphere. And then you have our atmosphere, which has specific elements depending on the height of the atmosphere. So for example, I think the gamma rays go up until the tropopause, or that's like 12 kilometers above us, the tropopause. So that's when the ultraviolet or gamma rays stop. Then the ionosphere itself is created from these gamma rays when they hit specific particles. Basically what happens is the gamma photon hits the particle in the atmosphere. And I said it before, there's three things that could happen. It could happen a photoelectric effect, or the whole photon can be absorbed by that specific atom, and then it could get into an ionized state, or into, actually not ionized, but excited state. And this is what you get on the auroras. So it's basically just the aurora happening. So the electron gives out energy, and this is the photon energy that's been given to it by the sun. The second part is what could happen is this photon hits another atom, and then what happens is, instead of absorbing the whole energy, it takes part of that energy and it just basically hits the atom, and then one of the electrons from that atom, from the electron Vivka, yeah, so one of these electrons gets removed from the atom, and this electron is part of the ionosphere. So basically, these are just electrons that are. I mean, this is just up until the maybe tropopause. So that's 12 kilometers. So maybe if you're in a plane, you're definitely going to receive a lot more radiation and a lot more. But this happens only when when the sun is radiating light towards the Earth. So this is happening during the day. During the night, we have another thing which is called recombination. So during the night, these electrons get recombined with the atoms, and they just disappear. That's actually really important. You know that the coldest time of the day, when is that? Do you know when it's the coldest? Just before sunrise. Yeah, and when is the hottest? Just before sunset. Yes. So the more the sun radiates heat, the more ionosphere we have in that specific area. And on the other side, when there's no heat, so the electrons just get recombined with the matter that's in the atmosphere. Does this make sense?